All right, kids. Today, very easy, very fun, kind of cool. We are going to find a way to find limits of quotients when the limits are of an indeterminate form. Huh? 0 over 0. Infinita over infinita. Those are what we like to refer to in the business as indeterminate. You cannot divide by 0. Even 0 can't be divided by 0, babe. Okay. So then the question is, well, what the heck, bro? Just look on Desmo's Chrome. Just use AI. No. 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 So we're going to be looking at a way to handle this as we go along. Also, 0 times 1, I'm sorry, 0 times 1. 0 times infinita is also a problem, as you might add. Well, I have 0 infinities. I have infinite number of zeros. Well, huh? Now, they were truly zeros, then yes, you can have a bunch of zeros and you get 0. The problem is we are approaching 0, ergo, not 0. Are you with me? This is huge. So then the question again is this, and we vaguely mentioned it earlier this year when we did this fellow, the sine of x over x, the limit as x approaches s0. See, es bueno. Now the way we're going to do this, we chatted about this when we did this, and we said, hey, the limit's 1. Well, why? When we looked at the graph and we said, all right, well, here's sine of x, here's sine of x, yes, and then here's x, and they're basically the same. That's right. The idea is they were basically approaching x at this, or x equals 0 at the same rate. There was a 1-to-1 ratio. So what we're going to talk about today is we're going to we hinted at that. They're approaching at the same rate. Today, that's what we're going to do. And so this is the question. If you have the limit as x approaches some c value of f of x over g of x, and you get either 0 over 0, infinita over infinita, or 1 times infinita, which isn't exactly in this fashion, but we'll talk more about that later on. But for right now, those two, okay, then, this is if then take the limit as x approaches c of the ratio of their derivatives. Notice I did not say take the derivative of the entire function. I did not say that. I said, so in other words, we will not, repeat, not be using the quotient rule. We'll be taking the limit of the top, the derivative of the top, the derivative of the bottom, and then comparing their speeds. And you're like, then what, Groom? Oh, if the limit as x approaches c of f prime of x divided by g prime of x is still 0, infinity over infinity, or 0 over 0, either one, then take the limit as x approaches c of f double prime over g double prime. And the idea here is, listen, they're going to the same direction. That's the first part, right? That's f and g. Take the derivative. That's how fast they're going, okay? Hey, they're going the same speed. Well, okay, let's take second derivative. The idea is, well, is one of them accelerating? Oh, that one's going to win. You with me? And we're going to wash, rinse, and repeat until we get, and repeat until we get something other than 0 over 0 or infinita over infinita. That's the game. It's easy money. This is referred to as lhopitals rule. And there's apostrophe in there somewhere. The hospitals rule. That's what the idiot said. I just like lhopitals rule. Okay. Anyway, it's lhopitals rule, and it's pretty daggum handy, and we'll use it again a little bit later on. So you need to be conversant with it. Again, it's not really rocket surgery. Okay, so let's do one here. Nice, easy one. We all know this one. The limit as x approaches infinity of x cubed minus 3x squared plus 5 over x to the 4 minus 3x cubed plus 6. And you're like, Groom, I know this is going to 0. You know it's going to 0. I know it's going to 0. Why? because the bottom is a bigger power of x in the numerator. You're absolutely right. So we know where we're going, but let's watch how L'Hopital works. You'll notice if you go infinity over, it's going to be this. Oh, that's indeterminate. Bro. So now let's take the limit as x approaches infinity of 3x squared minus 6x over 4x cubed minus 9x squared. Hey, look, it's infinity over infinity. Dude, take the derivative. Take the limit as x approaches infinity of the top, 6x minus 6, over the bottom, 12x squared minus 18x. Dude, it's still infinity over infinity. Oh, I gotta try again. Okay, Q 6 over 24x minus 18. The limit as x approaches infinity is 6 over infinity, which is 0. You with me, baby? 0. And you're like, that's it. I know. I know. Let's do another. Okay. What about that sine x over x? Oh, that's a good one. We should try it. Let's do this. The sine of x over x. Whoa. Hey, that's 0 over 0. That's no bueno, senor. That's no bueno. Hey, what is the limit as x approaches 0? Now, what's the derivative of sine? It's cosine. What's the derivative of x? It's 1. So we should be Gucci here. So what's the cosine of 0? The cosine of 0 is 1 over 1 is 1. Wait a minute. What about this fella? The limit as x approaches 0 of 1 minus the cosine of x over x. Well, well, Groom, that's 0 over 0. I know. That's no bueno. So let's take the derivative, shall we? X approaches 0, and you will get 1 in the basement. The top will become the sine of x, right? Right? Well, I should rewrite it out. So the limit as the sine of x over 1. And then what is that? We're going to get 0 over 1, which is 0, which was the correct answer. Okay? Okay. Now, I am not opposed to, I'm not above playing tricks on you on the test, Joseph Howard. So, if you're doing this and you're like, I think we're just doing L'Hopital all the time. What would happen if I gave you one where L'Hopital didn't apply? Well, it turns out it doesn't apply. You see how that works? Wait, you want to get the wrong answer? Yeah, you sure are. Oh, so what? You must check and see, Mr. Groom. I want to know, does it fit that indeterminate form? That's what we must do every time. Here's one, kids. The limit as x approaches negative infinity of the ln of x to the 4 plus 1 over squirt x. No, where did it go? Over x. Okay, well, I don't know. Infinity to the 4th is infinity, plus 1 is infinity. The ln of infinity is basically infinity. So we should, well, technically negative on the bottom. Either case, it's a problem. Okay? So let's take the derivative. So take the derivative. And so the top is going to be 1 over this garbage times the derivative of the inside, which is 4x cubed over 1. Now that simplifies to 4x cubed over 1x to the 4 plus 1. Now, if a guy puts infinity into there, what do you get? Well, you get negative infinity on top, and you get positive infinity on the bottom. Let's go. Hey, the limit as x approaches negative infinity. Hey, take the derivative, 12x squared. You can see where this is going, of course. You can see, and we got this. This is no big deal. Groom, can I simplify right now? You certainly could, because that's really just 3 over x, is it not? And if I do this, I get 3 over infinity, which is 0. But it's negative infinity. Shut up, it's still 0. Are you with me? So be aware of this. A lot of children right here will continue taking 2 more derivatives, right? Because they didn't simplify. If you simplify, which of course God knows you're able to do that because it's a ratio and that's what we can do. So yeah, it really saves yourself a little bit of effort and time if your head is not, stuck somewhere. So just pay attention to that. I'm not judging, I'm just saying. Okay? Hi, I'm Jay. Have we met? All right, cool. The limit as x approaches pi over thos of tan 3x over tan 5x. Well, let's see. pi over 2 times 3 is 3 pi over 2. The tangent of 3 pi over 2 is 0 over 0. This is not good. Oh, dear. So what do? Take the limit as x approaches pi over 2 of the derivatives. So it becomes the secant squared of 3x times 3 over 5 secant squared 5x. Now, what happens when you put pi over 2 into secant? Well, you get 1. You get 1. And what's 1 squared? Well, it's 1. So this answer becomes 3/5. Groom, can I check myself on Desmos? Well, you really should. Yeah, stupid. Yeah, go for it. Yeah, I mean that's kind of the whole point of why we use Desmos a lot because it's kind of a big deal. Okay. I don't know. Something happened today. I apparently I don't know, something's weird on my stupid computer all of a sudden, and so I don't know. It's kind of odd. 3x. What the heck is happening, bro? Tangent of 3x divide by tan 5x. Oops, 5x I said. 5x! Oh, shut up. Where's pi over 2, dog? Pi over 2 is not right there. Huh? Well, let's find x equals pi over 2. X equals pi divided by a dos. And if you look at pi over 2, oh, tangent of 5x, you dumbass. Hey, there it is. Woohoo! And look what we're approaching. We're approaching 1.666. Now, obviously that's a problem. By the way, every one of these points is really an F up. Not those ones, those ones. These ones here are F ups. There's no way that it can exist at that value, by the way. That's why we teach you how to do these things by hand. The computers get a little screwy. They just plug in numbers, and after a while they're like, it's good enough for government work, I think. And I don't honestly know because I'm not a programmer, nor do I ever want to be one on TV or otherwise because it sucks. Yeah, so we can play this game all day long. You got this one here. Some of these, by the way, are pretty straightforward. You should be able to kind of almost see them as you're going along. So e to the x minus 1 over sine x. Well, if you put 0 in, you get 1 minus 1 is 0. Sine of 0 is 0. That's a problem. And so take the limit of the derivatives. And so the derivative of the top is e to the x. The derivative of the bottom is cosine of x. You plug 0 in, you get 1 over 1 is uno. Okay. Oh, dude, we can play this game all day long, bro. I do want to do this one just for fun. There's one or two that are kind of like this that if you don't see them, it will freak you out. The limit of the ln of x over the square root of x as x approaches what? Well, 0 would be a problem, but that doesn't even exist at 0 on top. So it turns out it's infinity is what they want to know. Okay. So it can't be 0 because obviously there is no limit for ln at 0. It doesn't exist, right? So that would be problematic. So just be aware of that. The limit wouldn't exist there, so it pretty much had to be infinity. And so if you do this, that's infinity over infinity. Whoops, that's no good. The derivative is 1 over x. What is the derivative of that guy? Now remember, that's x to the 1/2. So it's going to be 1/2 x to the minus 1/2, which is 1 over 2 squirt x. But notice where that is. Don't screw that up. Now watch Mr. Groom play little musical chairs. That's 1 over x times 2 root x over 1, x to the 1/2. And you end up with 2 over root x. And so you get the limit as x approaches infinity. Well, there's 2 on top, duh. Infinity on the bottom, so the whole thing is going to 0. And again, a guy can go check himself real quick like and just see if that's true or not. ln x divided by squirt x. There he goes. Hey, look where that's going. Wee. Now, the guy gets out there far enough. let's see what happens. Let's this one here. Let's go out there around x equals 10,000 or something. Uh-oh. Oh, dear. Oh, my. You got here somewhere. Uh-oh. Yeah, oh, we're going to 0, aren't we? Is that what I said? Yeah, buddy. Yeah, buddy. Sometimes you have to get out there a long ways. Because remember, even if x equals 100, how close to infinity is that? Well, not very. So sometimes you kind of have to get out there a ways before you figure it out. Now, this one here, you're like, Groom, I only see the one division problem. True. What is cosecant doing, though? Cosecant's bouncing, so this one's kind of weird. So we need to get a common denominator. So if I do this, it's the limit as x approaches infinity of, well, this is 1 over x squared minus 1 over sine squared. Okay? So I need a common denominator. So that's going to be sine squared minus x squared over x squared sine squared. And I'm going to take the limit of that mess. Hey, what's sine doing? Hey, sine's bouncing back and forth between 1 and -1, right? But I'm squaring it, so back and forth between 1 and 0 in essence, yes? This guy, it just bounces back and forth between 0 and 1. Ditto down here on this guy, 0 and 1. It just bounces up and down. So it really has no impact on it. So the top's going to be like 1 minus infinity over infinity, basically, right? And so it's going to be infinity over infinity, basically. You with me on that? Okay. Technically, it should be probably negative infinity on top. But how do I know for sure? Well, I start taking derivatives. Are you with me? And so let's take some derivatives here. The limit of that as x approaches infinity. And then what do you get here? Well, you get, it's going to be 2 sine x cosine x minus 2x over, and then this is a chain rule down, or a product rule rather, sine squared plus x squared times 2 sine x cosine x, right? Something like that. Okay, now you take the derivative. Now what do you do? Well, okay, if I take the derivative now, I mean, if I integrate, take the limit now, again, this is just bouncing up and down, positive and negative 1 times 2, so positive and negative 2. This guy right here is doing what? Well, this guy here is going to be going to negative infinity. On the bottom, this is going to be going to infinity. And then this, of course, is infinity. And so you get infinity. Now, the bottom is a bigger infinity. Technically, yeah, it's going to be going to 0, but that's not why it's going to 0. One more derivative and see what happens. X approaches infinity. So the numerator is it's a cluster is what it is, honestly. And if you were on a deserted island and you just kind of punted and said, hey, the derivative of this is going to be more sines and cosines, if you said that, I probably wouldn't be upset. But in my classes, don't be lazy. So 2 sine x cosine x is equal to the same thing as saying the sine of 2x. You with me? So I can rewrite that as sine of 2x. So the derivative of that would be cosine of 2x times 2. Okay? And you're like, that's cute, minus 2. Okay? Over, ouch, the bottom, okay, this is another product rule. So that's going to be 2 sine squared x. And then plus, now that's going to be 2x times 2 sine x, well, times, and that's the same as sine of 2x. I'm going to write that. 2x sine of 2x. 2x. Okay, and then plus 2 cosine, 2x squared cosine 2x. Needless to say, the top is just going to be a constant of some sort divided by infinity. So the answer is it's going to 0. Okay, that's where this guy should be going. Okay, now let's see if we're right or not. Okay, so oops, what was the actual function? Oh yeah, it was 1 over x squared 1 divided by x squared minus 1 divided by parentheses sine x. Oh geez. Oh dear. Oh my. Squirt. No, not there. Not there. Get down there where you belong, loser. Right there. Oh, that's hot. Now let's zoom out a skosh. Mm-hmm. And, oh yeah, there it is. Yay. Now, this one actually... Hmm. 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 Mm-hmm. Hold that thought one moment, please. Mm-hmm. Oops. Oh, forgot about this one. I did forget about this one for a second. Initially, it was infinity over infinity. That's true. Down here, you got some infinities in it, but here's the problem on the bottom one down here, is that it's going to keep It's going to keep doing this all the time. Are you with me? And the fact that we're doing that all the time, this is why we like to check ourselves on the graph a little bit. The fact that it keeps oscillating like this means that there is no limit because it's never going to close in on something. You're like, Green, but you did the math. I understand. When you're done, it's always imperative to go check yourself. And what I forgot, was the fact that this thing oscillates forever. And I have to account for that. And I didn't because I'm a loser. I'm a horrible human being. Please don't hate me. Please don't hate me. Here's this one here. I think two more. We'll call it a day. You got this. This is pretty much the easiest thing on the friggin' planet to do. Boom. This is, what is this? What does this guy here? Well, this, as x approaches what? As x approaches infinity, this is infinity, and then 1 over infinity is basically what? Well, 1 over infinity is approaching 0, yeah? So this is the sine of 0. So this is basically saying in negative infinity times 0. Well, that's a problem, right? The guy cannot do that. Like, well, Groom, what do we do? What do we do? Well, exactly. So if you see something like, this times this, which is about the only thing you will ever see one of these, technically that is indeterminate. But what a guy needs to do is you need to put one of these guys in the basement. Either put him down here or put him under the other one. Either matter. I do the one that's easier. So for me, I think it's easier to rewrite this as, well, you dumbass. It's the sine of 1 over x and then x minus 1. Now, that's the same thing, right? I just wrote it differently. Does that make sense? I just wrote it like differently, I think. And now the top is 0. And now this is 1 over x down here. Well, what is, so this is the sine of 1 over x. And we said that's 0. And then over 1 over x, well, as this goes to infinity, this is also, yay! So now L'Hopital actually holds. So let's take the limit of their derivatives. How fast are they getting to 0? So it's the cosine of 1 over x times negative x to the minus 2, because it's a quotient or a chain rule, correct? X to the minus 2. You with me on that? Now, let's do that. Oh, wait, those cancel. They sure do. Now, what happens if this is infinity? If you put infinity, 1 over infinity is headed towards where? Well, it's headed towards 0. What is the cosine of 0, friends? 1. And again, you can go check himself if you want to. I feel very confident in that one. I don't always go check myself. There are some times when I think, well, I got this down, Groom. You're smart. Sometimes I'm stupid. I'm not that smart. But sometimes it's pretty straightforward. Oftentimes it's pretty straightforward. But once in a while, it's nice to go check yourself. Check yourself before you wreck yourself, etc. Now, let's do this one. Last one. But you said the last. I know what I said. Tangent of pi x over dos ln of x. Groom, this is a problem again. Well, it's a problem for two things. You didn't tell us where to go. So 1, there you go. Is that right? Right. So what's the tangent of pi over 2? That's 0. What's the... No, tangent of pi over 2 is infinity. That's right. And then the ln of 1 is 0. So... yeah, that's our problem. Then the question is, which would you rather do? Well, I would prefer to put tangent in the basement because it gives me something that I know how to fool with. Plus, if I put ln in the base, I get ln. I would get this if I put it in the basement. Ugh, and I don't want to do that very bad. You with me? But if I put this guy in the basement, it becomes cotangent pi x over 2. Now, if you do that, now I've rewrote. All I do is rewrote the thing, yes? So let's take the derivative now, shall we? If I take the derivative, that's going to be 1 over x over, what's the derivative of cotangent? It is negative cosecant squared pi x over 2 times pi over 2. Now, on top, you get 1. That's hot. Okay? Cosecant, right? It's the cosecant of pi over 2. Well, what is cosecant is sine. So it's the sine of pi over 2, kids, is 1. So 1 over that is 1. Squared is 1. With a negative in front is negative 1. So negative pi over 2, or negative 2 over pi. Let's see if we believe that. Oops, where's my desmos.com? Let's go have a look-see here. So that is, what did I say the problem was? Tangent pi x divided by 2 times the ln of x. That's hot. There we go. At pi over thos, x equals, no, x equals 1 rather. X equals 1, we're here. And look where we end up. We're at 0.7-ish, 0.72, right? Well, what is 2 divided by pi? Okay, so, actually, oh, yeah, 0.63. Yeah, I'd buy that for a nickel. Somewhere in that neighborhood of 0.63, right? You see that? Wee, 0.63-ish. Yeah, I'd buy that for a nickel. Nice. And so that's the game. That's it. That is lhopitals rule. Lhopitals rule. Okay? And that's it. That's all there is to it, friends. You got this. I have faith in you. Peace.